Hey sleepy friends, welcome back to Sleepy Science. Tonight we start with a sound you might not expect. A soft beep. Not from your phone. This one comes from a device that should not exist in the year 2580 BCE. A small screen glows in the pre-dawn darkness. Numbers flash across it. Latitude, longitude, elevation. An Egyptian surveyor holds a GPS receiver. He looks up at the stars, then down at the glowing device. The stars say one thing, the device says another. Both are right, but only one would have existed in ancient Egypt. The year is 2580 BCE. The Great Pyramid of Giza is rising from the desert. Workers have been building for years, millions of stone blocks, each weighing more than 2 tons. The pyramid must be perfectly square. Its sides must align with the cardinal directions: north, south, east, west. The base must be perfectly level. The angles must be precise. One mistake, and the entire structure could fail. Archaeologists have studied these pyramids for centuries. They measured every angle. They mapped every stone. What they found is astonishing. The Great Pyramid's base is almost perfectly square. The sides align with true north within a fraction of a degree. The base is level to within 2 centimeters across 230 meters. That is like leveling a football field so perfectly that no point is more than 2 centimeters higher or lower than any other. How did they do it? Without GPS. Without lasers. Without modern surveying tools. They used the stars, they used water, they used ropes and simple geometry. And they achieved precision that still amazes engineers today. In 2017, a team of archaeologists used laser scanning technology to measure the Great Pyramid with unprecedented accuracy. They discovered something remarkable. The 4 sides of the base are not perfectly straight. They curve inward slightly, creating what experts call a concave correction. This subtle curve was intentional. The Egyptians built it to compensate for the pyramid's massive weight. As the stone settled over time, the sides would naturally bulge outward. The curve prevents this. It is a design feature that shows incredible engineering foresight. But here is what makes this even more impressive. The Egyptians achieved this curve using only ropes, water, and careful observation. No computers. No advanced mathematics. Just knowledge passed down through generations of builders. But tonight, we imagine something different. What if ancient Egyptians had GPS? What if they could know their exact location, their exact elevation, their exact orientation, all from a small device? How would that change pyramid construction? Would it make it easier, faster, more precise? Or would it reveal something surprising about the methods they already used? For the next 2 hours we explore this thought experiment. We ground each claim in archaeological evidence. We use engineering principles. We apply surveying science. We examine how GPS works, what it requires, and how it would transform ancient construction. We trace how satellite navigation would reshape surveying, stone placement, and project coordination. Where evidence is uncertain, we say so. Where multiple outcomes are possible, we explore them all. The beep has sounded. The screen glows. A surveyor holds a device that connects to satellites that do not yet exist. Around this moment, experts wait. Archaeologists who understand ancient Egypt. Engineers who design modern structures. Surveyors who use GPS every day. They measure, analyze, and debate. The experiment has begun. First, let us understand what GPS actually is. GPS stands for Global Positioning System. It is a network of satellites orbiting Earth. There are about 30 satellites up there right now, constantly broadcasting signals. Your phone or a GPS receiver picks up these signals. By measuring how long the signals take to arrive, the receiver can calculate exactly where it is. The system needs at least 4 satellites to work properly. 3 satellites give you your position on Earth's surface, latitude and longitude. The 4th satellite gives you elevation, how high above sea level you are. All of this happens in seconds. The receiver calculates your position, often accurate to within a few meters. Some systems can be accurate to within centimeters. Modern surveyors use what they call real-time kinematic GPS. This system can measure positions to within 2 centimeters. That is incredibly precise. But here is something interesting. Even with this precision, modern construction projects still have tolerances. A building might be off by several centimeters, and that is considered acceptable. The Egyptians achieved similar precision without any of this technology. But here is the thing: GPS requires satellites, it requires radio signals, it requires electricity to power the receiver. It requires complex mathematics to calculate positions. None of these existed in ancient Egypt. So for our story, we need to imagine how GPS might arrive. Maybe a portal opens. Maybe advanced technology falls from the sky. Maybe time travelers bring it. For our purposes, it does not matter how it arrives. What matters is that it works. The satellites exist. The signals reach Earth. The receivers function, and the Egyptians can use them. But there is a catch. GPS receivers need power. They need batteries, or solar panels. They need to be charged. Ancient Egypt had no electricity. No power grids, no batteries like we know them. So how would they power GPS devices? The devices that arrive might come with solar panels. Ancient Egypt gets plenty of sunlight. A GPS receiver left in the sun could charge enough for a day of use. But what about cloudy days? What about night? GPS works at night, but the receiver still needs power. Maybe the devices come with hand-crank chargers. You turn a handle, and it generates electricity. Egyptian engineers, who already built complex machines, could probably figure out how to improve these. They might build larger versions powered by water wheels or even human labor. Not ideal, but it would work. The devices would also need to be durable. The desert is harsh. Sand gets everywhere. Heat can damage electronics. The devices would need to be built tough. Maybe they come in protective cases. Maybe they are designed to withstand extreme conditions. For our story, we assume the devices work reliably as long as they have power. Now, let us understand what the Egyptians actually did. How did they build the pyramids without GPS? This is one of the greatest mysteries in archaeology. And scientists have spent decades trying to figure it out. The first challenge was surveying. Before you build a pyramid, you need to mark out the base. You need to make it square. You need to align it with the cardinal directions. And you need to make it level. All of this, without modern tools. Archaeologists believe the Egyptians used several methods. For alignment, they likely used the stars. Specifically, they watched the stars that never set. These are called circumpolar stars. In the northern hemisphere, certain stars circle around the north celestial pole. They never rise or set. They just rotate around a fixed point in the sky. By observing these stars, the Egyptians could find true north. They would mark where a star rose and where it set. The midpoint between these 2 points would point north. They could do this with multiple stars to check their work. This method is remarkably accurate. It can align within a degree of true north. The Great Pyramid sides align with true north to within 0.05 degrees. That is incredibly precise. To put that in perspective, if you extended the north-south line of the pyramid, it would point to the North Pole, with an error of only about 3 arc minutes. That is like drawing a line a kilometer long, and being off by less than a meter at the end. Some researchers have suggested the Egyptians might have used a different method. Instead of watching stars rise and set, they could have used a tool called a merket. This was a simple device made of a plumb line and a sighting bar. By aligning the plumb line with a specific star at its highest point, surveyors could determine true north. Archaeologists have found merkets in tombs, suggesting they were important surveying tools. However, not all experts agree. Some argue that the merket was used for timekeeping, not surveying. The debate continues. What we know for certain is that whatever method the Egyptians used, it worked incredibly well. For leveling, the Egyptians likely used water. They would dig channels around the construction site, fill them with water. Water always finds its own level. So if the water surface is level at all points, the ground beneath must be level too. This is a simple but effective method. Archaeologists have found evidence of such channels at pyramid sites. At the Giza Plateau, researchers discovered a network of channels cut into the bedrock. These channels form a grid pattern around the pyramid bases. They are too shallow to be drainage systems, too regular to be natural formations. The most likely explanation is that they were used for leveling. Workers would fill these channels with water, then measure the water level at different points. If the water was at the same height everywhere, the ground was level. This method has a limitation though. Water evaporates. In the hot Egyptian sun, water levels could change quickly. Workers would need to refill the channels frequently. They would need to work quickly before the water disappeared. Despite these challenges, the method worked. The Great Pyramid's base is level to within 2 centimeters across its entire 230-meter width. For making the base square, they used geometry. The Egyptians knew about right angles. They knew that a triangle with sides of 3, 4, and 5 units forms a right angle. They could use ropes marked at these intervals to create perfect right angles. This is called a 3-4-5 triangle, and it is one of the oldest surveying tricks in the world. They would stretch a rope along one side of the square, mark it. Then use the 3-4-5 triangle method to create a right angle. Extend that line. Repeat. After 4 right angles, you have a square. Simple in theory, but incredibly difficult to do accurately over hundreds of meters. Yet they did it. The Great Pyramid's base is almost perfectly square. The sides differ in length by less than 20 centimeters, across 230 meters. That is an error of less than 0.1%. Modern construction standards would be impressed. Now imagine they had GPS. How would that change things? Let us think through each step of construction. Surveying the site would become instant. With GPS, finding your location takes seconds. You turn on the receiver, it tells you exactly where you are. Latitude, longitude, elevation. All in seconds. No need to observe stars, no need to wait for clear nights. You can survey during the day. You can survey in any weather. Imagine the time saved. Weeks of star observations compressed into minutes of GPS readings. But there is a problem. GPS tells you where you are relative to a modern coordinate system. The Egyptians did not use latitude and longitude. They used local landmarks. The Nile River. Specific mountains. Temple locations. GPS coordinates would be meaningless to them unless they could relate them to something familiar. Maybe the GPS devices come with maps. Digital maps showing the local area. The Egyptians could see their position on a map. They could see where the Nile is, where other pyramids are, where important landmarks are. This would help them understand GPS coordinates in context. But even with maps, GPS would transform surveying. Instead of spending weeks observing stars and measuring angles, surveyors could mark key points in minutes. They could place markers at the four corners of the pyramid base, record the GPS coordinates, then check alignment instantly. If the corners form a perfect square, the GPS coordinates would show it mathematically. GPS could also help with leveling. Modern GPS receivers can measure elevation to within centimeters. The Egyptians could place receivers at different points around the construction site. Compare elevations. Find the highest point. Then calculate how much to dig or fill at each location to make everything level. This would be much faster than using water channels. Water leveling works, but it is slow. You have to dig channels, fill them with water, wait for the water to settle, measure, adjust, repeat. With GPS, you could measure elevations in minutes. No digging required, no waiting for water to settle. But GPS has limitations. It works best with a clear view of the sky. If you are in a deep valley, or surrounded by tall buildings, satellite signals can be blocked. In ancient Egypt, this would not be much of a problem. The desert is flat. The sky is clear. But if workers were in a quarry, or a deep foundation, GPS might not work there. GPS also requires the receiver to be stationary for best accuracy. If you are moving, the position calculations become less precise. For surveying, this is usually fine. Surveyors stand still while taking measurements. But it means GPS would not help much with moving stones or coordinating workers in motion. Another limitation is that GPS gives you position but not orientation. It tells you where you are but not which way you are facing. To align the pyramid with north, you would still need to know direction. Modern GPS receivers often include compasses, but compasses need to be calibrated, and they can be affected by metal objects nearby. Maybe the GPS devices come with digital compasses. These use GPS movement to determine direction. You walk a few steps north. The GPS tracks your movement. From that, it calculates which way is north. This would work, but it requires movement. For a stationary surveyor marking a point, it might not help. So GPS would be incredibly useful for some tasks, but not all. It would revolutionize surveying and leveling. But alignment might still require traditional methods, or the devices would need additional features like compasses. Let us think about how GPS would change the actual construction process. Building a pyramid involves moving millions of stone blocks. Each block needs to be placed precisely. The pyramid must rise in layers. Each layer must be level. Each layer must be square. And the whole structure must maintain its shape as it gets taller. With GPS, workers could check their work constantly. After placing each layer of stones, surveyors could measure the corners. Check if they are still square. Check if the layer is level. If something is off, they could correct it before building higher. This would prevent small errors from accumulating. In traditional construction, a small mistake in the first layer becomes a bigger mistake in the 10th layer. By the time you reach the top, the pyramid might be noticeably crooked. With GPS, you could catch and fix errors early. GPS could also help coordinate work across the massive construction site. The Great Pyramid's base covers about 5.3 hectares. That is roughly the size of 7 football fields. Thousands of workers would be spread across this area. Coordinating them would be challenging. With GPS, supervisors could know exactly where each work crew is. They could send messages, coordinate stone deliveries, ensure different teams are working at the right elevations. This would improve efficiency and reduce mistakes. But here is an interesting thought. The Egyptians already achieved remarkable precision without GPS. Their methods worked. They were slow, but they were accurate. Would GPS actually improve the final result? Or would it just make construction faster? The Great Pyramid is already one of the most precisely built structures in history. Its alignment is nearly perfect, its leveling is nearly perfect. Its squareness is nearly perfect. Could GPS make it even better? Maybe, but the improvement would be small. The Egyptians were already operating near the limits of what is physically possible with stone construction. Consider this. Modern engineers use GPS to build skyscrapers. These buildings are incredibly precise. But they still have tolerances. They still settle. They still have imperfections. Technology helps, but it cannot eliminate the physical realities of construction. The Egyptians understood this. They built to incredible precision, but they accepted that perfect precision was impossible. GPS would not change this fundamental truth. GPS might make construction faster though. Instead of spending weeks surveying, they could do it in days. Instead of spending days leveling with water, they could do it in hours. This would save time. But would it save enough time to matter? Pyramid construction took decades. The Great Pyramid probably took about 20 years to build. Saving a few weeks on surveying would not change that much. The real time was spent quarrying stones, transporting them and placing them. GPS would not help much with those tasks. But GPS could help with logistics. Knowing exact locations could help plan transport routes. Workers could mark the best paths from quarries to the construction site. They could avoid obstacles. They could find the flattest routes. This would make moving stones easier and faster. GPS could also help with organization. The construction site was massive. Different teams worked on different parts. With GPS, supervisors could track where each team is, ensure they are not interfering with each other, coordinate their work more effectively. Now let us think about what GPS would reveal about the Egyptians' existing methods. If they had GPS, they could compare their star-based alignment with GPS coordinates. They could see how accurate their methods really were. This would be fascinating. The Egyptians achieved 0.05-degree alignment with stars. GPS would show them that their method worked. It would validate their techniques. But it might also reveal small errors they did not know about. For example, the Great Pyramid's sides are not perfectly aligned. They are off by a tiny amount. With GPS, the Egyptians could measure this precisely. They could see exactly how much error exists, and they could correct it. But here is the thing. The existing alignment is already incredibly good. The error is so small that it might not matter. Stone blocks are not perfectly uniform. The pyramid settles over time. Small imperfections are inevitable. GPS might reveal errors that are too small to fix with the available tools. GPS would also teach the Egyptians about Earth itself. GPS coordinates are based on a mathematical model of Earth's shape. The Egyptians did not know Earth is round. They thought it was flat. GPS would show them that positions are described using a curved coordinate system. This might confuse them at first. But over time, they might realize that Earth is curved. They might notice that distances work differently than they expected. This could lead to early discoveries about geography and Earth's shape. GPS elevation measurements would also be interesting. GPS measures height above sea level using a reference model. The Egyptians did not have a concept of sea level in the same way. Their elevation measurements were relative to local landmarks. GPS would give them absolute elevations. They could see that the pyramid site is a certain number of meters above sea level. They could compare this to other locations. This would help them understand the landscape in new ways. But GPS has a limitation here. It measures elevation relative to a mathematical model of Earth's shape. This model is not perfect. Local variations in gravity affect the model, so GPS elevation can be off by several meters in some places. For pyramid construction, this might not matter much. The Egyptians needed relative elevations. Is point A higher than point B? GPS could tell them that. The absolute elevation above sea level was less important. Now let us think about the cultural and historical implications. How would GPS change Egyptian society? How would it affect knowledge and power? GPS is a tool, but it is also a source of knowledge. It reveals information about location, time, and space. In ancient Egypt, this knowledge was power. Priests and scribes controlled knowledge. They were the ones who understood astronomy, mathematics, and surveying. If GPS devices were widely available, this knowledge would spread. Ordinary workers could know their exact location. They could understand surveying principles. They could participate in construction planning. This would shift power away from the elite. But maybe the pharaoh would control GPS devices. Maybe only royal surveyors would have them. This would maintain the existing power structure. GPS would make construction more efficient, but knowledge would still be restricted. Or maybe GPS devices would be too common to control. If thousands of devices appeared across Egypt, the pharaoh could not restrict them all. Workers would learn to use them. Knowledge would spread. This could lead to social changes. GPS would also affect how knowledge is transmitted. Traditional surveying methods required years of training. Apprentices learned from masters. Knowledge passed down through generations. With GPS, the methods become simpler. Anyone can learn to use a GPS receiver in hours. This would make surveying more accessible, but it might also make traditional knowledge less valuable. Star-based alignment methods might be forgotten. Water leveling techniques might be lost. Future generations might depend entirely on GPS, losing the ability to work without it. This is a real concern with modern technology too. As we rely more on GPS, we lose traditional navigation skills. Sailors who once navigated by stars now depend on GPS. If GPS fails, they might be lost. The same could happen in ancient Egypt. But GPS would also enable new possibilities. With precise location data, the Egyptians could create accurate maps. They could survey the entire kingdom. They could plan infrastructure projects. They could coordinate military campaigns. GPS would transform many aspects of Egyptian society, not just pyramid construction. Let us think about what modern scientists have learned from studying the pyramids. Archaeologists use GPS today to map pyramid sites. They create precise 3D models. They measure every angle. They document every stone. This has revealed new details about construction methods. For example, scientists discovered that the Great Pyramid's sides are slightly concave. They curve inward by about 60 centimeters. This was intentional. The Egyptians built this curve to compensate for the pyramid's weight. As stones settle, the sides would bulge outward. The curve prevents this. GPS helped make this discovery. By mapping the pyramid precisely, scientists could measure the curve. They could see that it was too regular to be accidental. It was a deliberate design feature. If the Egyptians had GPS during construction, they could have measured this curve themselves. They could have verified that each layer maintained the correct curvature. This would have made construction more precise. But they achieved the curve without GPS. They used traditional methods. And it worked. This shows that their techniques were sophisticated. GPS would make things easier, but it would not be necessary. Now let us think about the bigger picture. What does this thought experiment teach us? What does it reveal about technology, precision, and human achievement? First, it shows that precision is possible with simple tools. The Egyptians achieved near-perfect alignment using stars and ropes. They did not need satellites. They did not need computers. They needed knowledge, skill, and patience. GPS would make precision easier, but it would not make it more possible. The limits are not technological, they are physical. Stone blocks are not perfectly uniform. Foundations settle. Materials expand and contract with temperature. No amount of technology can eliminate these physical realities. Second, it shows that technology changes methods, but not necessarily outcomes. GPS would revolutionize surveying. But the final pyramid might not be much better than what the Egyptians already built. The improvement would be marginal. This is an important lesson. New technology does not always mean better results. Sometimes, traditional methods work just as well. Sometimes, they work better. The key is understanding when to use new tools, and when to stick with proven methods. Third, it shows that knowledge matters more than tools. The Egyptians understood geometry, they understood astronomy, they understood construction. This knowledge let them build pyramids. GPS would give them new tools, but the knowledge would still be essential. Without understanding how GPS works, the Egyptians could not use it effectively. They would need to learn coordinate systems. They would need to understand elevation models. They would need to interpret the data. Technology is useless without knowledge. Fourth, it shows that precision has limits. No matter how advanced the tools, perfect precision is impossible. Materials have imperfections. Measurements have errors. Construction has tolerances. The goal is not perfection, but good enough. The Egyptians understood this. They built to incredible precision, but they accepted small errors. They knew that some imperfections are inevitable. GPS would not change this. It would just make the acceptable errors smaller. Finally, it shows that human achievement is remarkable. The Egyptians built the Great Pyramid 400–500 years ago, without modern tools, without modern knowledge, without GPS, and it still stands. It is still one of the most precisely built structures in history. GPS would make their job easier, but it would not make their achievement less impressive. The skill, the knowledge, the dedication required would still be extraordinary. Technology is a tool. Human ingenuity is the real marvel. So what if ancient Egyptians had GPS? They would build pyramids faster, they would achieve slightly better precision, they would coordinate work more efficiently. But the pyramids would still be pyramids. They would still be massive. They would still be precise. They would still be remarkable. The real question is not whether GPS would help. It would. The real question is whether it would change what the pyramids represent. Would they still be symbols of human achievement? Would they still inspire wonder? Would they still amaze us 400–500 years later? We think the answer is yes. Technology enhances human ability. It does not replace it. The Egyptians would still need to quarry stones. They would still need to transport them. They would still need to place them precisely. GPS would help, but the work would still be work. The achievement would still be an achievement. And maybe that is the most important lesson. Tools change. Methods evolve. But human ingenuity remains constant. Whether using stars or satellites, ropes or receivers, the goal is the same. To build something lasting. To create something precise. To achieve something remarkable. The beep has sounded. The screen glows. A surveyor holds a device that connects to satellites that do not yet exist. But the pyramid rises anyway, stone by stone. Layer by layer, year by year. With or without GPS, the work continues, the achievement endures. Let us dive deeper into how GPS actually works. Understanding the technology helps us see what it could and could not do for the Egyptians. GPS satellites orbit Earth at an altitude of about 20,000 kilometers. They travel at incredible speeds, completing one orbit every 12 hours. Each satellite carries atomic clocks. These clocks are accurate to within a few nanoseconds. That precision matters because GPS calculates position by measuring time. Here is how it works. A satellite broadcasts a signal that includes the time the signal was sent. Your GPS receiver picks up this signal. It measures how long the signal took to arrive. Since radio signals travel at the speed of light, the receiver can calculate the distance to the satellite. Distance equals speed times time. The speed of light is constant, so if you know the time, you know the distance. But distance alone is not enough. You need multiple satellites. With one satellite, you know you are somewhere on a sphere around that satellite. With two satellites, you know you are somewhere on a circle where the two spheres intersect. With three satellites, you know you are at one of 2 points where the three spheres intersect. With 4 satellites, you know your exact position. The fourth satellite also gives you elevation. This all happens in milliseconds. Your phone receives signals from multiple satellites simultaneously. It calculates distances. It solves the geometry. It determines your position, all while you are walking, driving, or standing still. For the Egyptians, this would be revolutionary. They would not need to understand the physics. They would not need to know about atomic clocks or orbital mechanics. They would just need to know how to use the device, turn it on, read the numbers, mark the location. Simple. But there are complications. GPS signals are weak. They travel 20,000 kilometers through space. By the time they reach Earth, they are incredibly faint. Your phone can pick them up, but the signal is easily blocked. Buildings block GPS. Trees block GPS. Even your own body can block GPS if you hold the device wrong. In ancient Egypt, this would be less of a problem. The desert is flat. The sky is clear. There are no tall buildings, no dense forests. The main challenge would be in quarries or deep foundations. But for most surveying work, GPS would work perfectly. Another challenge is accuracy. Consumer GPS, like what is in your phone, is accurate to within about 5 meters. That is good enough for navigation, but not for precise surveying. Professional surveyors use more advanced systems. They use what is called differential GPS. This involves a base station at a known location. The base station measures GPS errors. It broadcasts corrections. Other receivers use these corrections to improve their accuracy. With differential GPS, surveyors can achieve centimeter-level accuracy. That is precise enough for construction. The Egyptians would need this level of precision for pyramid building, so we assume the GPS devices that arrive include differential GPS capability. Maybe they come with base stations. Maybe they use some other method. For our story, we assume they can achieve centimeter accuracy. Now let us think about what the Egyptians would actually do with GPS. How would they use it in practice? Imagine a surveyor arriving at the Giza Plateau in 2580 BCE. The site has been chosen. The pharaoh wants a pyramid here. The surveyor's job is to mark out the base. With traditional methods, this would take weeks. With GPS, it could take hours. The surveyor turns on the GPS receiver. It connects to satellites. It calculates position. The screen shows coordinates. But what do these numbers mean? The Egyptians do not use latitude and longitude. They use local reference points. The Nile River, the temple complex, specific landmarks. Maybe the GPS devices come with a calibration feature. The surveyor goes to a known location. maybe the base of an existing pyramid. He marks that location in the GPS. Now the device knows where it is relative to local landmarks. It can translate GPS coordinates into Egyptian reference systems. Or maybe the devices come with preloaded maps, digital maps showing the Nile Valley, the pyramids, the temples. The surveyor can see his position on the map. He can see where he needs to go. He can mark locations visually, not just with numbers. Either way, the surveyor begins marking the pyramid base. He goes to what will be the northeast corner. He places a marker. The GPS records the coordinates. He moves to the northwest corner, places a marker, records coordinates. Southeast corner, southwest corner. 4 corners marked. 4 coordinates recorded. Now comes the check. Do these 4 points form a perfect square? The GPS can calculate this instantly. It measures the distances between corners. It measures the angles. If the corners form a square, the distances will be equal. The angles will be 90 degrees. The GPS can verify this mathematically. But what if something is off? What if one corner is slightly out of place? The GPS can show exactly how much error exists. It can show which direction to move the marker. The surveyor adjusts, rechecks, adjusts again, until the square is perfect. This process would take hours instead of weeks. The time savings would be enormous. But would it make the final pyramid better? That is the real question. Let us think about the actual construction process. How would GPS help once building begins? The Great Pyramid contains about 2.3 million stone blocks. Each block weighs between 2.5 and 15 tons. The largest blocks, at the base, weigh up to 80 tons. Moving these blocks was the real challenge. GPS would not help much with that. But GPS could help with placement. Each block needs to be positioned precisely. The layers need to be level. The corners need to align. GPS could verify this constantly. Imagine workers placing the first layer of stones. After each section is complete, a surveyor checks with GPS. Are the corners still square? Is the layer level? If something is off, workers can adjust before continuing. This would prevent errors from accumulating. In traditional construction, a small error in the first layer becomes a bigger error in later layers. By the time you reach the top, the pyramid might be noticeably crooked. With GPS, you catch errors early. You fix them before they compound. But here is something interesting. The Great Pyramid is not perfectly straight. Its sides curve inward slightly. This curve was intentional. The Egyptians built it to compensate for settling. With GPS, they could measure this curve precisely. They could verify that each layer maintains the correct curvature. This would be valuable. But the Egyptians achieved the curve without GPS. They used traditional methods. And it worked. So GPS would make the process easier, but not necessarily better. Let us explore the specific techniques the Egyptians used for stone cutting and placement. Understanding these methods helps us see where GPS would and would not help. The Egyptians cut stones using copper chisels and stone hammers. Copper was the hardest metal available to them. Iron had not yet been discovered, or at least was not widely used. Copper chisels could cut limestone, but the work was slow. Workers had to strike the chisel repeatedly. They had to be careful not to crack the stone. Archaeologists have found evidence of this process. Quarry sites show marks from chisels. They show where workers cut blocks from the bedrock. The marks are regular, showing that workers had a system. They cut channels around blocks. Then they inserted wooden wedges. They soaked the wedges with water. The wood expanded, splitting the stone along the channels. This process took time. A single block might take days to extract. Workers had to be patient. They had to be careful. One mistake could ruin a valuable block. GPS would not help with this at all. It would not make chisels sharper. It would not make hammers heavier. It would not speed up the cutting process. The physical work would remain the same. But GPS could help with planning. Workers could map quarry sites precisely. They could identify the best locations for extraction. They could plan the layout of blocks. They could coordinate multiple work crews. This would improve efficiency slightly, but not dramatically. Once blocks were cut, they had to be shaped. Workers used stone hammers to smooth the surfaces. They checked flatness using straight edges. They checked squareness using the 3-4-5 triangle method. This took time. Each block had to be carefully shaped to fit its position. GPS would not help with shaping either. It would not make hammers more effective. It would not speed up the smoothing process. The work would remain manual and time-consuming. But GPS could help with quality control. Workers could measure block dimensions precisely. They could verify that blocks meet specifications. They could check the blocks fit together correctly. This would improve quality, but the time savings would be small. Transporting blocks was another major challenge. Workers dragged blocks on sledges. They used ropes and levers. They poured water on the sand to reduce friction. This made dragging easier, but still required enormous effort. Archaeologists have found evidence of this. A wall painting shows workers dragging a large statue. The painting shows water being poured in front of the sledge. This was a clever technique. Wet sand is more slippery than dry sand. It reduces friction, making dragging easier. GPS would not help with dragging. It would not make blocks lighter. It would not reduce friction. It would not eliminate the need for workers. The physical effort would remain the same. But GPS could help with route planning. Workers could map the terrain precisely. They could identify the flattest routes. They could avoid obstacles. They could plan the most efficient paths. This would make transportation slightly more efficient, but not dramatically so. Once blocks arrived at the construction site, workers had to move them up the pyramid. They probably used ramps. Archaeologists have found evidence of ramps at pyramid sites. These ramps were made of mud, brick, and rubble. They were built up as the pyramid rose. The ramps were probably straight, not spiral. A straight ramp would be simpler to build. It would be easier to drag stones up, but it would require more material. A spiral ramp would use less material, but would be more complex to build. Archaeologists debate which type of ramp was used. Evidence is limited. But most agree that some form of ramp was necessary. Moving 80-ton blocks up a 146-meter pyramid without ramps would be nearly impossible. GPS would not help with ramp construction. It would not make ramps less steep. It would not reduce the amount of material needed. It would not speed up the building process. The work would remain physical and time-consuming, but GPS could help with ramp planning. Workers could measure elevations precisely. They could calculate the optimal ramp angle. They could plan ramp locations. They could ensure ramps are straight and level. This would improve ramp quality, but the time savings would be small. Placing blocks was the final challenge. Workers positioned each block carefully. They checked alignment. They checked level. They ensured blocks fit together tightly. This required precision and patience. With traditional methods, workers used plumb lines and sighting rods. They checked alignment by sighting along edges. They checked level using water channels. This took time. Workers had to be careful. One mistake could affect the entire structure. With GPS, workers could check positions instantly. They could measure block locations precisely. They could verify alignment immediately. They could ensure blocks are in the correct position. This would make placement faster and more accurate. But the time savings would still be small. Most of the time was spent moving blocks, not checking positions. GPS would save minutes per block, not hours. Over millions of blocks this adds up, but not dramatically. However, GPS could improve quality significantly. With constant checking, workers could catch errors early. They could fix problems before they compound. They could ensure precision throughout construction. This would result in a more accurate pyramid. But the Great Pyramid is already incredibly accurate. The improvement would be marginal. GPS would make a good pyramid slightly better, but it would not transform the result. So GPS would help with some tasks but not others. It would make surveying faster. It would improve precision. It would enable better quality control. But it would not speed up the physical work. It would not reduce the effort required. It would not eliminate the fundamental challenges of pyramid construction. The real question is whether these improvements would matter. Would a slightly faster, slightly more precise pyramid be worth the technology? Or would the Egyptians be better off with their traditional methods? We think the answer depends on the context. If GPS devices are rare and valuable, the Egyptians might use them only for the most important projects. If GPS devices are common, they might use them for everything. But in either case, the fundamental work would remain the same. The pyramids would still be built by hand, the stones would still be heavy, the ramps would still be steep. The work would still take decades. GPS would help, but it would not eliminate the challenge. And maybe that is the point. Technology enhances human ability. It does not replace it. The Egyptians would still need skill, they would still need knowledge, they would still need dedication. GPS would make the job easier, but it would not make it easy. The achievement would still be remarkable, the pyramids would still inspire wonder. They would still amaze us 400 or 500 years later. GPS would not change that. Let us think about coordination. The Great Pyramid's construction site was massive. Thousands of workers spread across hectares of desert. Coordinating them would be challenging. With GPS, supervisors could track where each work crew is. They could see which teams are working on which sections. They could ensure teams are not interfering with each other. They could coordinate stone deliveries. They could manage the flow of materials. This would improve efficiency, but how much? The real bottlenecks were not coordination, they were quarrying stones, transporting stones, placing stones. GPS would not help with these tasks. Quarrying stones was hard physical work. Workers used copper chisels and stone hammers. They cut blocks from limestone bedrock. This took time. GPS would not make it faster. Transporting stones was also slow. Workers dragged blocks on sledges. They used ramps to move them up the pyramid. This took enormous effort. GPS would not reduce that effort. Placing stones required precision. Workers positioned each block carefully. They checked alignment. They checked level. This took time. GPS could make this faster, but not dramatically so. So GPS would help, but it would not revolutionize construction. The time savings would be in surveying and verification, not in the actual building process. Let us explore the internal structure of the Great Pyramid. Understanding what is inside helps us see where GPS would be most useful. The Great Pyramid is not solid. It contains a complex network of passages and chambers. The entrance is on the north face, about 17 meters above ground level. A descending passage leads down into the bedrock. This passage was probably used during construction. Workers could access the interior to build the burial chamber. The burial chamber is located deep inside the pyramid. It is made of granite blocks from Aswan. These blocks are massive. Some weigh over 50 tons. Moving them into position was an incredible feat. Workers had to drag them through narrow passages. They had to position them precisely. One mistake could block the entire passage. Above the burial chamber is a series of relieving chambers. These chambers reduce the weight on the burial chamber ceiling. They are made of granite blocks arranged in layers. The design is ingenious. It distributes the pyramid's weight, preventing the ceiling from collapsing. The pyramid also contains a grand gallery. This is a tall, narrow passage that leads to the burial chamber. It is about 47 meters long and 8.5 meters high. The walls are made of polished limestone. They are precisely aligned. The gallery served both functional and symbolic purposes. GPS would be incredibly useful for building these internal structures. Surveyors could measure passage alignments precisely. They could verify that passages are straight. They could ensure chambers are level. They could check that everything fits together correctly. With traditional methods, building internal structures was challenging. Workers had limited space. They could not use the same surveying techniques as for the exterior. They had to work in cramped conditions. They had to rely on simple tools and careful measurement. With GPS, surveyors could work more effectively. They could measure positions even in narrow passages. They could verify alignments instantly. They could ensure precision throughout construction. This would make building internal structures faster and more accurate. But GPS has limitations in enclosed spaces. Satellite signals might not reach deep inside the pyramid. Workers might need to use other methods for interior work. Or they might need to use GPS receivers at the surface, then transfer measurements inside. Either way, GPS would help with internal construction. It would improve precision. It would speed up surveying. It would enable better quality control. The internal structures would be more accurate, even if the improvement is small. Now let us think about the workforce. How many people built the Great Pyramid, and how would GPS help coordinate them? Archaeologists estimate that about 20,000 to 30,000 workers built the Great Pyramid. This is a massive workforce. Coordinating them would be challenging. Workers were organized into teams. Each team had specific tasks. Some teams quarried stones. Some teams transported stones. Some teams placed stones. Some teams built ramps. Some teams prepared the site. The organization was hierarchical. Overseers managed teams. Supervisors coordinated multiple teams. Administrators planned the overall project. This structure enabled efficient coordination, even without modern communication. GPS would enhance this coordination. Supervisors could track where each team is working. They could see which areas are complete. They could identify bottlenecks. They could redirect workers as needed. This would improve efficiency and reduce delays. But the real coordination challenge was not location, it was timing. Teams had to work in sequence. Quarrying had to happen before transport. Transport had to happen before placement. Ramps had to be built before blocks could be moved up. GPS would not help with this sequencing. That required planning and communication, not positioning. However, GPS could help with planning. Supervisors could map the entire construction site. They could see where work is happening. They could plan sequences more effectively. They could coordinate multiple activities simultaneously. This would improve overall efficiency. GPS could also help with resource management. Supervisors could track where materials are. They could see which quarries are active. They could coordinate stone deliveries. They could ensure materials arrive when needed. This would reduce waiting time and improve productivity. But again, the time savings would be small. Most of the time was spent in physical work, not in coordination. GPS would save hours, not days. Over a 20-year project, this adds up, but not dramatically. Now let us think about what GPS would teach the Egyptians. What would they learn from this technology? First, they would learn about Earth's shape. GPS coordinates assume Earth is round. The Egyptians thought Earth was flat. GPS would show them that positions are described using a curved coordinate system. This might confuse them at first. But over time they might realize that Earth is curved. They might notice that distances work differently than expected. They might discover that the shortest path between 2 points is not always a straight line. This could lead to early discoveries about geography. The Egyptians might map their kingdom more accurately. They might understand the relationship between different regions. They might plan infrastructure projects more effectively. Second, they would learn about precision. GPS shows positions to within centimeters. This level of precision might inspire them. They might strive for greater accuracy in other areas. They might develop new measurement techniques. They might improve their construction methods. Third, they would learn about time. GPS requires precise timing. The satellites use atomic clocks. The receivers must track time accurately. This might lead the Egyptians to develop better timekeeping devices. They might improve their calendars. They might understand time in new ways. But here is the thing. The Egyptians already had sophisticated knowledge. They understood astronomy. They understood geometry. They understood construction. GPS would add to this knowledge, but it would not replace it. Let us think about the social implications. How would GPS change Egyptian society? Knowledge was power in ancient Egypt. Priests and scribes controlled knowledge. They understood astronomy, mathematics, and surveying. This gave them influence. It gave them status. If GPS devices were widely available, this knowledge would spread. Ordinary workers could learn surveying. They could understand positioning. They could participate in construction planning. This would shift power away from the elite. But maybe the pharaoh would control GPS devices. Maybe only royal surveyors would have them. This would maintain the existing power structure. GPS would make construction more efficient, but knowledge would still be restricted. Or maybe GPS devices would be too common to control. If thousands of devices appeared across Egypt, the pharaoh could not restrict them all. Workers would learn to use them. Knowledge would spread. This could lead to social changes. This is similar to what happened with the printing press. When books became widely available, knowledge spread, power shifted, society changed. GPS might have a similar effect in ancient Egypt. But there is a downside. As people rely more on GPS, they might forget traditional methods. Star-based alignment might be lost. Water leveling techniques might be forgotten. Future generations might depend entirely on GPS, losing the ability to work without it. This is a real concern with modern technology. As we rely more on GPS, we lose traditional navigation skills. Sailors who once navigated by stars now depend on GPS. If GPS fails, they might be lost. The same could happen in ancient Egypt. But GPS would also enable new possibilities. With precise location data, the Egyptians could create accurate maps. They could survey their entire kingdom. They could plan infrastructure projects. They could coordinate military campaigns. GPS would transform many aspects of Egyptian society, not just pyramid construction. Let us think about specific examples. How would GPS change different aspects of pyramid building? First, site selection. The Egyptians chose pyramid sites carefully. They looked for solid bedrock. They considered the relationship to the Nile. They thought about visibility and symbolism. GPS would not change these considerations, but it would help verify sites. Surveyors could check elevation. They could measure slopes. They could assess the terrain more accurately. Second, foundation preparation. Before building, workers prepared the foundation. They leveled the bedrock. They cut channels for leveling. This took time. With GPS, They could measure elevations precisely. They could identify high and low points. They could calculate exactly how much to dig or fill. This would make foundation preparation faster and more accurate. Third, stone placement. Workers placed stones carefully. They checked alignment. They checked level. This took time. With GPS, they could verify positions instantly. They could check alignment constantly. They could catch errors early. This would improve precision and reduce rework. Fourth, quality control. Throughout construction, supervisors checked the work. They measured angles. They checked levels. They verified alignment. With GPS, this would be faster and more accurate. Supervisors could check more frequently. They could catch problems earlier. They could ensure quality throughout the process. Fifth, documentation. The Egyptians did not leave detailed construction records. We do not know exactly how they built the pyramids. With GPS, they could record everything. They could document each step. They could create detailed maps. Future generations would have a complete record of construction methods. This would be valuable for historians. But it might not help the Egyptians themselves. They already knew how to build pyramids. Documentation would preserve knowledge, but it would not improve construction. Let us compare the Great Pyramid with other ancient structures. How does it measure up? And how would GPS help with similar projects? The Great Pyramid was not the only pyramid built in ancient Egypt. There are over 100 pyramids in Egypt. Most are smaller than the Great Pyramid. But they all required similar construction techniques. They all needed surveying, leveling, and precise stone placement. The Pyramid of Khafre, built next to the Great Pyramid, is slightly smaller but still massive. It stands about 136 meters tall. Its base is about 215 meters square. It was built with similar precision. Its sides align with true north to within a few arc minutes. Its base is leveled to within centimeters. The Pyramid of Menkaure, the smallest of the three Giza pyramids, is about 65 meters tall. Its base is about 105 meters square. Despite its smaller size, it was built with the same care and precision. The Egyptians did not cut corners on smaller projects. GPS would help with all these pyramids. It would make surveying faster. It would improve precision. It would enable better coordination, but the benefits would be similar for all projects. GPS would not make small pyramids easier to build than large ones. The fundamental challenges would remain the same. The Egyptians also built other structures besides pyramids: temples, palaces, cities. These structures required similar construction techniques. They needed surveying. They needed leveling. They needed precise stone placement. GPS would help with all of these. For example, the Temple of Karnak is a massive complex. It covers over 200 acres. It contains hundreds of columns. Each column had to be positioned precisely. Each had to be aligned correctly. GPS would help with this positioning. It would make surveying faster. It would improve alignment. It would enable better coordination. But again, the time savings would be small. Most of the time was spent in physical work, not in surveying. GPS would save hours, not days. The construction would still take years. The Egyptians were not the only ancient builders. Other civilizations built impressive structures. The Romans built aqueducts. The Greeks built temples. The Incas built stone cities. How would GPS help with these projects? The Romans built aqueducts that carried water for hundreds of kilometers. These aqueducts had to maintain a precise slope. Too steep, and water would flow too fast. Too shallow, and water would not flow at all. The slope had to be just right. GPS would be incredibly useful for building aqueducts. Surveyors could measure elevations precisely. They could calculate slopes accurately. They could ensure the aqueduct maintains the correct gradient throughout its length. This would make aqueduct construction faster and more accurate. The Greeks built temples with precise proportions. The Parthenon, for example, uses mathematical ratios throughout. Every column, every beam, every detail follows specific measurements. The precision is remarkable. GPS would help with temple construction. Surveyors could measure positions precisely. They could verify proportions accurately. They could ensure everything fits together correctly. This would improve precision, even if the time savings are small. The Incas built stone cities high in the Andes. They cut stones so precisely that they fit together without mortar. The joints are incredibly tight. Modern engineers still marvel at this precision. GPS would help with Inca construction. Surveyors could measure stone positions precisely. They could verify alignments accurately. They could ensure stones fit together correctly. This would improve precision, even if the work remains manual. So GPS would help with many ancient construction projects. It would make surveying faster. It would improve precision. It would enable better coordination. But it would not eliminate the fundamental challenges. The physical work would remain. The time required would still be substantial. Now let us think about limitations. What could GPS not do? GPS cannot move stones. It cannot cut blocks. It cannot transport materials. These tasks require physical effort. GPS would not reduce that effort. GPS cannot design pyramids. It cannot determine the best shape or size. These decisions require knowledge and judgment. GPS would not provide that. GPS cannot coordinate workers directly. It can show where people are, but it cannot tell them what to do. That requires supervisors and communication. GPS would help, but it would not replace human management. GPS cannot eliminate physical limitations. Stone blocks are heavy, ramps are steep, workers get tired. GPS would not change these realities. So GPS would be a tool, not a solution. It would make some tasks easier, but it would not eliminate the fundamental challenges of pyramid construction. Let us explore the detailed construction techniques the Egyptians used. Understanding these methods in depth helps us see exactly where GPS would help and where it would not. Archaeologists have studied pyramid construction for centuries. They have examined quarry sites. They have analyzed tool marks. They have reconstructed construction methods. What they have discovered is remarkable. The quarrying process began with selecting the right stone. Workers looked for limestone that was uniform in color and texture. They avoided stones with cracks or flaws. This selection process was crucial. A bad stone could ruin an entire section of the pyramid. Once a suitable area was found, workers marked out blocks. They used red ochre to draw lines on the bedrock. These lines showed where to cut. The blocks were typically rectangular, about 1.5 meters long, 1 meter wide, and 0.5 meters tall. This size was manageable. Larger blocks were used for special purposes, like the burial chamber. Cutting began with creating channels around the block. Workers used copper chisels to cut grooves. These grooves were about 5 centimeters deep. They followed the marked lines precisely. This was slow work. A single channel might take hours to cut. Once channels were complete, workers inserted wooden wedges. They placed wedges along the channels at regular intervals. Then they soaked the wedges with water. The wood expanded as it absorbed water. This expansion created pressure. The pressure split the stone along the channels. This technique was clever. It used the natural properties of wood and water. It required no explosives. It required no complex machinery, just simple tools and knowledge of materials. After blocks were extracted, they had to be shaped. Workers used stone hammers to smooth the surfaces. They checked flatness using straight edges. A straight edge was a long piece of wood or stone. Workers would place it against the block surface. If light showed through gaps, the surface was not flat. Workers would continue hammering until the surface was smooth. They checked squareness using the 3-4-5 triangle method. They would measure 3 units along one edge, 4 units along another edge, 5 units along the diagonal. If these measurements matched, the corner was square. This method is still used today by carpenters. Shaping blocks took time. Each block had to be carefully worked. Workers had to be patient. They had to be precise. One mistake could ruin a valuable block. Once blocks were shaped, they had to be transported. This was one of the most challenging aspects of construction. Workers dragged blocks on sledges. A sledge was a wooden platform with runners. Blocks were placed on the sledge. Ropes were attached. Workers pulled the ropes. Archaeologists have found evidence of this process. A wall painting from the tomb of Jehudhotep shows workers dragging a large statue. The painting shows 172 workers pulling ropes. The statue weighs about 60 tons. This gives us an idea of the effort required. Workers also used a clever technique to reduce friction. They poured water on the sand in front of the sledge. Wet sand is more slippery than dry sand. It reduces friction significantly. This made dragging easier but still required enormous effort. For blocks from farther away, the Egyptians used boats. They loaded blocks onto barges. They floated them down the Nile. The Nile was the highway of ancient Egypt. It connected quarries to construction sites. This was more efficient than dragging, but still slow. Once blocks arrived at the construction site, workers had to move them up the pyramid. They probably used ramps. Archaeologists have found evidence of ramps at pyramid sites. These ramps were made of mud, brick, and rubble. They were built up as the pyramid rose. The exact design of the ramps is still debated. Some archaeologists think they were straight ramps built against one side. Others think they were spiral ramps wrapping around the pyramid. Still others think they were a combination of both. Straight ramps would be simpler to build. They would be easier to drag stones up. But they would require more material. A straight ramp to the top of the Great Pyramid would be over 1.5 kilometers long. That is a lot of material. Spiral ramps would use less material. They would wrap around the pyramid, but they would be more complex to build. They would require careful planning. They would need to maintain the correct slope throughout. Most archaeologists now think the Egyptians used a combination. Straight ramps for the lower levels, spiral ramps for the upper levels. This would balance simplicity and efficiency. Moving blocks up ramps was hard work. Workers pulled ropes. They used levers to help. They worked in teams. Coordination was essential. One mistake could send a block tumbling down. This would be dangerous and wasteful. Once blocks reached their level, workers positioned them. This required precision. Each block had to fit tightly with its neighbors. Gaps would weaken the structure. Misalignment would create problems. Workers checked alignment using plumb lines. A plumb line is a weight on a string. Gravity makes it hang straight down. Workers could use it to check if walls were vertical. They could use it to check if corners were square. They checked level using water channels. They would dig small channels around the work area, fill them with water, check that the water level was the same everywhere. If it was, the ground was level. Positioning blocks took time. Workers had to be careful, they had to be patient, they had to work together. One mistake could affect the entire structure. Now let us think about what archaeologists have discovered about pyramid construction. Recent findings have revealed new details about the process. In 2013, archaeologists discovered a papyrus that describes pyramid construction. This papyrus was found at the Red Sea port of Wadi al-Jarf. It dates to the reign of Khufu, the pharaoh who built the Great Pyramid. It is the oldest papyrus ever found. The papyrus describes how stones were transported from Tura to Giza. Tura is across the Nile from Giza. The papyrus mentions boats and canals. It describes the organization of work crews. It gives us a rare glimpse into the actual construction process. The papyrus mentions that workers were organized into teams. Each team had a name. Each team had specific tasks. This organization was crucial for coordinating such a large project. Archaeologists have also discovered worker villages near pyramid sites. These villages housed the workers who built the pyramids. They were not slaves, as once thought. They were skilled workers who were paid for their labor. The villages show that workers had good living conditions. They had bakeries, they had breweries, they had medical facilities. This suggests that workers were valued. They were not expendable labor. Archaeologists have also found evidence of the tools used. Copper chisels, stone hammers, ropes, levers. These tools were simple, but effective. They enabled workers to build structures that still amaze us today. Recent excavations have also revealed details about the internal structure of pyramids. Archaeologists have used robots to explore narrow passages. They have discovered hidden chambers. They have found evidence of construction techniques. For example, archaeologists discovered that the Great Pyramid contains relieving chambers above the burial chamber. These chambers reduce the weight on the ceiling. They are made of granite blocks arranged in layers. The design is ingenious. It distributes the pyramid's weight, preventing the ceiling from collapsing. Archaeologists have also discovered that the pyramid's sides are slightly concave. This curve was intentional. The Egyptians built it to compensate for settling. As stones settle over time, the sides would naturally bulge outward. The curve prevents this. This discovery was made using modern technology. Archaeologists used laser scanning to measure the pyramid precisely. They discovered the curve was too regular to be accidental. It was a deliberate design feature. Archaeologists have also studied the pyramid's alignment. They have confirmed that the sides align with true north to within 0.05 degrees. This is incredibly precise. It shows that the Egyptians had sophisticated surveying techniques. They have also studied the pyramid's leveling. They have confirmed that the base is level to within 2 centimeters across 230 meters. This is remarkable precision. It shows that the Egyptians had effective leveling methods. Archaeologists have also discovered evidence of the workforce. They have found inscriptions that name work crews. They have found evidence of how workers were organized. They have found evidence of how the project was managed. All of this evidence helps us understand how the pyramids were built. It shows that the Egyptians had sophisticated techniques. It shows that they had effective organization. It shows that they had remarkable skill. GPS would help with many of these techniques. It would make surveying faster. It would improve precision. It would enable better coordination. But it would not eliminate the fundamental challenges. The physical work would remain. The time required would still be substantial. The Egyptians achieved remarkable results with simple tools. GPS would enhance their capabilities, but it would not replace their skill. The achievement would still be impressive. The wonder would still be there. Let us explore more archaeological discoveries that reveal how the pyramids were built. Recent findings have provided new insights into construction methods. In 2018, archaeologists discovered a ramp system at a quarry in Hatnub, Egypt. This quarry provided alabaster for the pyramids. The ramp system shows how workers moved massive stones. The ramp was cut into the bedrock. It had steps on either side. Workers could use ropes and levers to move stones up the ramp. This discovery provides direct evidence of how the Egyptians moved heavy materials. The ramp at Hatnub shows sophisticated engineering. It was designed to reduce the effort required. The steps provided footholds for workers. The angle was carefully calculated. Too steep, and stones would be impossible to move. Too shallow, and the ramp would be too long. The Egyptians found the right balance. Archaeologists have also discovered evidence of the tools used for cutting stone. At quarry sites, they have found copper chisels. These chisels show wear patterns that reveal how they were used. Workers struck the chisels with stone hammers. The repeated impacts gradually cut through the limestone. The chisels themselves are remarkable. They were made of copper, which is relatively soft, but the Egyptians hardened the copper by hammering it. This process, called work hardening, makes copper stronger. It enabled the chisels to cut limestone effectively. Archaeologists have also found evidence of the measurement tools used. They have discovered cubit rods. A cubit was the standard unit of measurement in ancient Egypt. It was about 52.5 centimeters, roughly the length from elbow to fingertip. Workers used cubit rods to measure blocks. They ensured that blocks were the correct size. They have also found evidence of leveling tools. They have discovered wooden levels. These were simple devices. A wooden beam with a plumb line attached. Workers could use them to check if surfaces were level. Simple, but effective. Archaeologists have also studied the organization of work crews. They have found inscriptions that name specific crews. For example, one crew was called Friends of Khufu. Another was called Drunkards of Menkore. These names suggest that crews had identities. They were not just anonymous workers. The organization was hierarchical. Overseers managed crews. Supervisors coordinated multiple crews. Administrators planned the overall project. This structure enabled efficient coordination. It allowed thousands of workers to work together effectively. Archaeologists have also discovered evidence of the workforce's diet. They have found animal bones in worker villages. They have found evidence of bread and beer production. The diet was adequate. Workers were well fed. This suggests that workers were valued. They were not expendable. Recent excavations have also revealed details about the pyramid's internal structure. Archaeologists have used muon tomography to scan the pyramid. Muons are particles that can pass through stone. By detecting muons, scientists can map the internal structure. This technique has revealed hidden chambers and passages. In 2017, scientists discovered a large void above the Grand Gallery. This void is about 30 meters long. Its purpose is unknown. It might be a relieving chamber, it might be a construction feature, it might be something else entirely. The discovery shows that the pyramid still holds secrets. Archaeologists have also studied the pyramid's casing stones. These were the smooth, white limestone blocks that covered the pyramid. Most of these stones are gone now. They were removed over the centuries, but a few remain at the base. These remaining stones show incredible precision. They fit together so tightly that a knife blade cannot fit between them. The casing stones were cut and polished with incredible care. Workers used stone tools to smooth the surfaces. They achieved a mirror-like finish. The pyramid would have gleamed in the sunlight. It would have been visible for miles. Archaeologists have also discovered evidence of the pyramid's original appearance. They have found fragments of casing stones. They have studied how the stones were arranged. They have reconstructed what the pyramid looked like when it was new. The pyramid was not just a structure, it was a work of art. Every detail was carefully planned. Every surface was carefully finished. The precision was not just functional, it was also aesthetic. GPS would help with achieving this precision. Surveyors could measure positions precisely. They could verify alignments accurately. They could ensure that every stone was in the right place. This would improve quality, even if the time savings are small. But GPS would not change the fundamental process. Workers would still need to cut stones carefully. They would still need to shape them precisely. They would still need to polish them to perfection. The skill and dedication would remain. Archaeologists have also discovered evidence of the pyramid's construction timeline. They have found inscriptions that date different phases of construction. They have studied how the pyramid was built over time. The construction took about 20 years. This is an incredible achievement. The construction was not continuous. There were probably pauses. Workers might have stopped during the annual Nile flood. They might have paused for religious festivals. They might have taken breaks for other reasons. But overall, the work continued steadily for 2 decades. GPS would not change this timeline dramatically. It would save time on surveying. It would improve precision. It would enable better coordination. But the fundamental work would remain. The construction would still take years. However, GPS might enable more efficient use of time. Workers could work during more hours of the day. They would not need to wait for clear nights to check alignment. They could work in any weather. This might compress the timeline slightly, but not dramatically. Archaeologists have also discovered evidence of the pyramid's purpose. It was not just a tomb, it was a complex structure with multiple functions. It served religious purposes. It served political purposes. It served symbolic purposes. The pyramid's alignment with the stars was not accidental, it was intentional. The Egyptians believed that the pharaoh's soul would travel to the stars. The pyramid's alignment helped guide this journey. This spiritual dimension adds to the pyramid's significance. GPS would help with achieving this alignment. Surveyors could align the pyramid precisely with the stars. They could verify the alignment constantly. They could ensure that the spiritual purpose was fulfilled. This would be important to the Egyptians. But GPS would not change the spiritual significance. The pyramid would still be a sacred structure. It would still serve its religious purpose. GPS would be a tool, not a replacement for meaning. Let us think about what modern scientists have learned from studying the pyramids. How has GPS helped us understand ancient construction? Modern archaeologists use GPS to map pyramid sites precisely. They create detailed 3D models. They measure every angle. They document every feature. This has revealed new details about construction methods. For example, scientists discovered that the Great Pyramid sides are slightly concave. They curve inward by about 60 centimeters. This was intentional. The Egyptians built this curve to compensate for settling. GPS helped make this discovery. By mapping the pyramid precisely, scientists could measure the curve. They could see that it was too regular to be accidental. Scientists also discovered that the pyramid's base is not perfectly square. The sides differ slightly in length. The longest side is about 20 centimeters longer than the shortest. This small difference was probably not intentional. It might be due to measurement errors or settling. But it shows that even the Egyptians were not perfect. GPS has also helped scientists understand the pyramid's orientation. The sides align with true north to within 0.05 degrees. This is incredibly precise. Scientists used GPS to verify this alignment. They confirmed that the Egyptians achieved near-perfect orientation using only stars. These discoveries show that the Egyptians were remarkable builders. They achieved precision that still amazes engineers today. GPS helps us understand their methods, but it also shows us what they achieved without it. Let us explore the actual construction process in more detail. How did the Egyptians move those massive stones? And how would GPS help or not help with this? The Great Pyramid's stones came from several sources. Most of the limestone blocks came from quarries near Giza. These quarries are still visible today. Archaeologists have found evidence of the quarrying process. Workers used copper chisels and stone hammers. They cut blocks from the bedrock. This was slow, hard work. Some stones came from farther away. The white limestone casing stones came from Tura, across the Nile. The granite blocks in the burial chamber came from Aswan, over 800 kilometers away. Transporting these stones was a major undertaking. For local stones, workers probably dragged them on sledges. Archaeologists have found evidence of this. A wall painting from the tomb of Jehutihotep shows workers dragging a statue on a sledge. The statue weighs about 60 tons. It took 172 workers to move it. This gives us an idea of the effort required. For stones from farther away, the Egyptians used boats. They loaded stones onto barges. They floated them down the Nile. Then they unloaded them near the construction site. This was more efficient than dragging, but still slow. Once stones arrived at the site, workers had to move them up the pyramid. They probably used ramps. Archaeologists have found evidence of ramps at pyramid sites. These ramps were made of mud, brick and rubble. They were built up as the pyramid rose. Workers dragged stones up these ramps using ropes and sledges. GPS would not help with any of this. It would not make stones lighter. It would not make ramps less steep. It would not reduce the number of workers needed. The physical effort would remain the same. But GPS could help with planning. Workers could map the best routes from quarries to the construction site. They could identify obstacles. They could find the flattest paths. They could plan ramp locations more effectively. This would make transportation slightly more efficient, but not dramatically so. GPS could also help with coordination. Supervisors could track where stone deliveries are. They could coordinate multiple work crews. They could ensure stones arrive when needed. This would improve logistics, but again, the time savings would be small. The real time was spent in the physical work. Quarrying stones took months. Transporting stones took months. Placing stones took months. GPS would not change this. The construction would still take decades. But let us think about what GPS could do during construction. How would it help with the actual building process? Workers placed stones in layers. Each layer had to be level. Each layer had to be square. The corners had to align. This required constant checking. With traditional methods, surveyors checked alignment using plumb lines and sighting rods. They checked level using water channels. This took time. Workers had to wait while surveyors measured. Then they could continue building. With GPS, surveyors could check instantly. They could measure positions in seconds. They could verify alignment immediately. Workers would not have to wait as long. This would make construction slightly faster. But the time savings would be small. Most of the time was spent moving stones, not checking alignment. GPS would save hours, not days. Over a 20-year construction project, this would not make a huge difference. However, GPS could improve quality. With constant checking, workers could catch errors early. They could fix problems before they compound. This would result in a more precise pyramid. But the Great Pyramid is already incredibly precise. The improvement would be marginal. Let us think about specific construction challenges. How would GPS help with each one? First, foundation preparation. Before building, workers prepared the bedrock. They leveled it. They cut channels for leveling. This took weeks. With GPS, they could measure elevations precisely. They could identify exactly where to dig. They could calculate exactly how much to remove. This would make foundation preparation faster and more accurate. Second, corner alignment. The pyramid's corners had to be perfectly square. Workers checked this constantly. With GPS, they could verify squareness instantly. They could measure distances between corners. They could check angles. This would make alignment faster and more accurate. Third, layer leveling. Each layer had to be perfectly level. Workers checked this with water channels. With GPS, they could measure elevations at multiple points. They could verify levelness instantly. This would make leveling faster and more accurate. Fourth, side straightness. The pyramid's sides had to be straight. Workers checked this with sighting rods. With GPS, they could measure positions along each side. They could verify straightness instantly. This would make checking faster and more accurate. Fifth, overall shape. The pyramid had to maintain its shape as it rose. Workers checked this constantly. With GPS, they could measure the entire structure. They could verify the shape at any point. This would make quality control faster and more accurate. So GPS would help with all these tasks. But the time savings would be small. The real time was spent in physical work, not in checking. Now, let us think about what GPS would reveal. What would the Egyptians learn about their own methods? If they had GPS, they could compare their star-based alignment with GPS coordinates. They could see how accurate their methods really were. This would be fascinating. The Egyptians achieved 0.05-degree alignment with stars. GPS would show them that their method worked. It would validate their techniques. But it might also reveal small errors they did not know about. For example, the Great Pyramid's sides are not perfectly aligned. They are off by a tiny amount. With GPS, the Egyptians could measure this precisely. They could see exactly how much error exists, and they could correct it. But here is the thing. The existing alignment is already incredibly good. The error is so small that it might not matter. Stone blocks are not perfectly uniform. The pyramid settles over time. Small imperfections are inevitable. GPS might reveal errors that are too small to fix with the available tools. GPS would also teach the Egyptians about measurement itself. They would see that positions can be described with numbers. They would learn about coordinate systems. They would understand precision in new ways. This might inspire them to improve their measurement techniques. They might develop better tools. They might create more accurate methods. They might push the limits of what is possible. But they were already pushing those limits. The Great Pyramid is one of the most precisely built structures in history. GPS would help them go further, but they were already operating near the physical limits of stone construction. Let us think about the cultural impact. How would GPS change Egyptian society beyond pyramid construction? First, mapping. With GPS, the Egyptians could create accurate maps of their entire kingdom. They could survey the Nile Valley. They could map the desert. They could document their territory precisely. This would be valuable for administration, military planning, and infrastructure development. Second, navigation. The Egyptians traveled extensively. They traded with other regions. They sent military expeditions. GPS would help with navigation. Travelers could know their exact location. They could find their way more easily. This would make travel safer and more efficient. Third, agriculture. The Egyptians depended on the Nile's annual flood. They needed to know when the flood would come. They needed to measure fields accurately. GPS could help with both. It could provide precise timing. It could measure field boundaries accurately. This would improve agricultural planning. Fourth, construction. The Egyptians built many structures besides pyramids, temples, palaces, cities. GPS could help with all of these. It could improve surveying. It could speed up construction. It could ensure precision. This would transform Egyptian architecture. Fifth, astronomy. The Egyptians were skilled astronomers. They tracked stars, they developed calendars, GPS would add to this knowledge. It would provide precise timing. It would help with observations. It would enable new discoveries. So GPS would have far-reaching effects. It would not just change pyramid construction. It would transform many aspects of Egyptian society. But there would be challenges. The Egyptians would need to learn how to use GPS. They would need to understand coordinate systems. They would need to interpret the data. This would require education and training. The devices would need maintenance. They would need power. They would need protection from the harsh desert environment. This would require infrastructure and resources. The technology might be misused. People might become too dependent on it. They might forget traditional skills. This could be a problem if the technology fails. But overall, GPS would be a powerful tool. It would enhance Egyptian capabilities. It would enable new possibilities. It would transform society in ways we can only imagine. Let us think about specific scenarios. What would happen in different situations? Scenario 1. GPS devices appear suddenly. Millions of them fall from the sky. They are distributed randomly across Egypt. Some go to priests, some go to workers. Some go to farmers. What happens? Knowledge spreads quickly. People learn to use GPS. They discover new capabilities. They share information. Traditional power structures might weaken. New possibilities emerge. Scenario 2. GPS devices are controlled by the pharaoh. Only royal surveyors have them. Knowledge remains restricted. Construction becomes more efficient, but society does not change much. Scenario 3. GPS devices are rare. Only a few exist. They are highly valued. People compete for access. This creates new power dynamics. It might lead to conflict. Each scenario would have different outcomes. The impact depends on how GPS is distributed and controlled. But regardless of the scenario, GPS would change pyramid construction. It would make surveying faster. It would improve precision. It would enable new possibilities. The pyramids would still be built, but the process would be different. And that is the key point. GPS would change methods, but not outcomes. The pyramids would still be pyramids. They would still be massive. They would still be precise. They would still be remarkable. Let us think about how modern construction uses GPS. Understanding current applications helps us see what the Egyptians could achieve. Modern construction projects use GPS extensively. Surveyors use it to map sites. Engineers use it to position structures. Contractors use it to verify work. GPS has become essential for large projects. For example, when building a skyscraper, surveyors use GPS to mark foundation corners. They use it to verify that the building is square. They use it to check that floors are level. GPS enables precision that would be difficult to achieve otherwise. But even with GPS, modern construction has tolerances. Buildings are not perfectly square. Floors are not perfectly level. Measurements have errors. Construction has limits. GPS helps, but it does not eliminate these realities. The Egyptians faced similar challenges. They built to incredible precision, but they accepted small errors. They knew that perfect precision was impossible. GPS would not change this. It would just make the acceptable errors smaller. Modern construction also takes time. Even with GPS and modern machinery, building a skyscraper takes years. The physical work remains substantial. Technology helps, but it does not eliminate the fundamental challenges. The Egyptians would face the same situation. GPS would make their work easier, but it would not eliminate the challenges. The pyramids would still take decades to build. The physical effort would still be enormous. The achievement would still be remarkable. Let us think about specific modern construction techniques. How do they compare to ancient methods? And how would GPS help the Egyptians adopt similar techniques? Modern construction uses prefabrication. Components are built off-site, then assembled on-site. This speeds up construction. It improves quality. It reduces waste. The Egyptians could use similar techniques with GPS. They could build components at quarries. They could shape stones precisely. They could verify dimensions with GPS. Then they could transport components to the site. They could assemble them quickly, knowing that everything fits. This would improve efficiency. But it would require organization. It would require planning. It would require coordination. GPS would help with all of these, but the fundamental work would remain. Modern construction also uses cranes and heavy machinery. These tools make moving materials easier. They reduce the physical effort required. They speed up construction. The Egyptians did not have cranes. They used ramps and sledges. They used ropes and levers. They used human and animal power. GPS would not change this. It would not provide cranes. It would not eliminate the need for physical effort. But GPS could help with planning. Workers could map the site precisely. They could plan ramp locations. They could coordinate material movements. They could optimize the construction process. This would improve efficiency, even without modern machinery. Modern construction also uses computer-aided design. Engineers create detailed 3D models. They plan every detail before construction begins. This improves accuracy. It reduces errors. It speeds up the process. The Egyptians did not have computers. They used drawings and models. They used experience and knowledge. They used trial and error. GPS would not provide computers. It would not enable 3D modeling. It would not eliminate the need for planning. But GPS could help with verification. Workers could check that construction matches plans. They could verify dimensions precisely. They could ensure accuracy throughout the process. This would improve quality, even without computer-aided design. So GPS would help the Egyptians in many ways. It would make surveying faster. It would improve precision. It would enable better coordination. But it would not provide modern machinery. It would not eliminate physical work. It would not transform construction completely. The fundamental challenges would remain. The pyramids would still be built by hand. The stones would still be heavy. The ramps would still be steep. The work would still take decades. GPS would help, but it would not eliminate the challenge. And maybe that is the point. Technology enhances human ability. It does not replace it. The Egyptians would still need skill. They would still need knowledge. They would still need dedication. GPS would make the job easier, but it would not make it easy. The achievement would still be remarkable. The pyramids would still inspire wonder. They would still amaze us 400-500 years later. GPS would not change that. Now let us think about the bigger picture. What does this thought experiment teach us? First, it shows that precision is possible with simple tools. The Egyptians achieved near-perfect alignment using stars and ropes. They did not need satellites. They did not need computers. They needed knowledge, skill, and patience. GPS would make precision easier, but it would not make it more possible. The limits are not technological, they are physical. Stone blocks are not perfectly uniform. Foundations settle. Materials expand and contract with temperature. No amount of technology can eliminate these physical realities. Second, it shows that technology changes methods, but not necessarily outcomes. GPS would revolutionize surveying. But the final pyramid might not be much better than what the Egyptians already built. The improvement would be marginal. This is an important lesson. New technology does not always mean better results. Sometimes, traditional methods work just as well. Sometimes, they work better. The key is understanding when to use new tools and when to stick with proven methods. Third, it shows that knowledge matters more than tools. The Egyptians understood geometry. They understood astronomy. They understood construction. This knowledge let them build pyramids. GPS would give them new tools, but the knowledge would still be essential. Without understanding how GPS works, the Egyptians could not use it effectively. They would need to learn coordinate systems. They would need to understand elevation models. They would need to interpret the data. Technology is useless without knowledge. Fourth, it shows that precision has limits. No matter how advanced the tools, perfect precision is impossible. Materials have imperfections. Measurements have errors. Construction has tolerances. The goal is not perfection but good enough. The Egyptians understood this. They built to incredible precision, but they accepted small errors. They knew that some imperfections are inevitable. GPS would not change this. It would just make the acceptable errors smaller. Finally, it shows that human achievement is remarkable. The Egyptians built the Great Pyramid 400–500 years ago, without modern tools, without modern knowledge, without GPS, and it still stands. It is still one of the most precisely built structures in history. GPS would make their job easier, but it would not make their achievement less impressive. The skill, the knowledge, the dedication required would still be extraordinary. Technology is a tool. Human ingenuity is the real marvel. So what if ancient Egyptians had GPS? They would build pyramids faster. They would achieve slightly better precision. They would coordinate work more efficiently. But the pyramids would still be pyramids. They would still be massive. They would still be precise. They would still be remarkable. The real question is not whether GPS would help. It would. The real question is whether it would change what the pyramids represent. Would they still be symbols of human achievement? Would they still inspire wonder? Would they still amaze us 400–500 years later? We think the answer is yes. Technology enhances human ability. It does not replace it. The Egyptians would still need to quarry stones. They would still need to transport them. They would still need to place them precisely. GPS would help, but the work would still be work. The achievement would still be an achievement. And maybe that is the most important lesson. Tools change, methods evolve, but human ingenuity remains constant. Whether using stars or satellites, ropes or receivers, the goal is the same: to build something lasting, to create something precise, to achieve something remarkable. The beep has sounded. The screen glows. A surveyor holds a device that connects to satellites that do not yet exist, but the pyramid rises anyway, stone by stone, layer by layer, year by year. With or without GPS, the work continues. The achievement endures.